All right, so we had our fun on the chat talking about all the snow we've had and where we're at, and the fact that some people, because they're not here, didn't get a lot of snow, and so they're laughing at us. Anyway, the temperature's nice and warm. Well, at least it's above zero, and it feels really nice out there. So, couple of things with regards to your term exam. I have still working on the marking, so you may not have a grade yet because there's a couple of TAs that are still going through and marking their exams, their assigned questions. But on that note, I have actually moved the term exam into a folder further down in the Blackboard directory. That folder is called exams. It's got a green heading, and I've also uploaded the free response answers, or my answers to those free response questions. And so you can go on there at your convenience and have a look at that. I believe you should be able to see the correct answers for the computer marked questions, and your grades, once everything is done, will be there as well. I think that's it for the announcements for today, and I think I answered everyone's questions on the chat before starting to record this. Not sure what that was about, but I'm just going to ignore it. I do want to go here because we are going to do a demonstration really quickly. Is there any problem in the Blackboard? No, not that I know of. Everything should be working just fine as far as I can figure out. There is an acid-base indicator out there that's actually a mixture of acid-base indicators, and it's called universal indicator because it gives you a rainbow of colors that dictates the pH from around pH 2 to pH 12. So carefully selecting and mixing acid-base indicators together, we actually get this color spectrum. The reason why I've put this up is because we're going to be using it right now. And that looks like it is correct. So you need to tell me if the camera starts messing up. The beaker just has water in it, and this is universal indicator. So if this is just pure water, it should have a pH somewhere around 7, 6 point something, which is green. And it is a green solution, so that's positive. And I just need to, much being able to pour, add about an equal amount actually looks pretty good. Doesn't need to be exact, but it's pretty close actually. And I actually need more water, so while my container fills up, I'll go grab a lab coat. Now, the water looks cloudy right now because it is aerated, and so those bubbles are going to settle in just a few seconds, which allows me to get a lab coat and gloves on. Good. So what I want to do is I want to put about 1,600 mils into each of these. And where are we at right now? 1,000? Is there 600 in here? There's a little bit more. Need to dump out just a tiny bit of this. Because I want to add to one of the solutions a buffer. And this is pH 7 buffer. So the solution is reasonably buffered now, but it's going to keep the pH that it's at, about a pH of 7. 1600 grams. Good. So the flask on the left-hand side is just pure water, about a pH of 7, 6.5. This one, well, pH of 7 since the colors are about the same. The one on the right-hand side has got a good amount of buffer in it. Now, we've already looked at the chemistry involving CO2. We talked about it in relation to the body and how we use that to regulate the pH of our body, the blood, using carbonic acid buffer. This is carbon dioxide, solid carbon dioxide, and I'm going to add some carbon dioxide to each of the flasks. And I want to get about the same amount of carbon dioxide at each of them, and we'll see what happens. Now what we're looking for is changes in pH, which we observe as changes in color. And you can see that the flask on the left-hand side very quickly went acidic, and the right-hand side is staying green. Now we've exhausted the buffer, and that one is also changing color and becoming yellow as well. And now those solutions are somewhat acidic. I don't know if you can see on the camera, but it is fairly obvious that the one on the left-hand side is slightly redder than the one on the right. Because of the buffer that we have added to this, it's limiting how low the pH can go. Now, I actually don't know what makes up the pH 7 buffer. I should probably find that out. What we're going to do on the left-hand side is I'm going to make it go basic, and what you're going to see is that as it goes back to acidic, it doesn't get this dark. It actually won't get as dark as the orange on the right-hand side. There we've made it blue. And we can add some more dry ice to each of those. And you can see the one on the left-hand side is now slowly going back to being green like the glove and becoming more and more acidic. No matter how long we let that go, it actually will never get to be the color orange that is on the right-hand side, because we now have created, with the addition of sodium hydroxide, we've created a carbonate buffer. And so it's going to limit the pH to be somewhere in the range of about 5.5, 6, whereas the one on the right-hand side is around 4 and a bit. So we can come back and look at those in a few minutes, but that is an demonstration of the effects of buffers and how they moderate the pH initially, and then the second one is how adding sodium hydroxide also creates a buffer, and with that created buffer, we limit how low the pH can go, in this case due to the carbonic acid buffer created there. So if we look at those colors that we have over there, one of the one is orange, and the other one is yellow-green, yellow-orange color. So one of the ones is in the range of about pH 4, just under, and the other is a pH of about 5-ish. So just go back and look at them for just a second. Again, the one on the left-hand side still has not gotten any thing closer to the orange color due to the carbonic acid buffer that's there. Now I do have a question for you. You've probably been told in your classes that dry ice is really, really, really cold. Probably had this in high school. You've also been told that you shouldn't touch dry ice with your hands because it'll freeze your tissue. Yet I am holding dry ice right now in my hand. And my question for you is, how am I able to hold the dry ice without, is seemingly in contravention of what you've been told in high school? Do you have an answer for me? Why can I do that? Put your answers into the chat. I am hoping that you agree that I'm a superhero, or not that I have to help shovel, honestly. Ah, superhero. Excellent. Thank you, thank you, thank you. But I'm not going to try flying today, or any day. So, but really, why was I able to hold the dry ice in my hand and not freeze my tissue, my skin? The answer is because I'm warm-blooded and I have circulation in my hand. So as long as the dry ice doesn't stay in the same location, it doesn't take my tissue below 0 degrees. Okay, so that was a demo on buffers. Should have happened the other day, but wasn't feeling well, wasn't here, didn't have actually have all the equipment anyway, the chemicals. Now we've gone through that. What we need to do is not that, is go here and skip ahead a lot of slides. Last day we looked through titrations, and we compared strong acid, strong base titrations and weak acid and weak base titrations. We saw similarities when they were titrating as something that is strong, and similarities when you were titrating something that was weak. The idea of a buffered region before the equivalence point, and the entities in a weak acid base titration, the product of the analyte after the equivalence point is ultimately also a weak base or acid, and so it affects the pH, whereas in a strong system the pH is 7 because the conjugate doesn't have any basic or acidic properties. We looked at polyprotic titrations and how that would be very difficult to do with an indicator. And the one thing I want to emphasize, because it is going to be one of your assignment questions, is the pH of HA minus we can't determine because when HA minus being amphiprotic, by definition, there are two dominant equilibria. There's the acidic version and the basic version of that equilibrium that affect the pH, and we don't know how to deal with that in class, but we can get a good estimate of the equivalence point, or the pH at this equivalence point, by taking the midpoint between pKa1 and pKa2. And the last thing we did is looked at the steps to calculating a titration curve, and like we had in ice tables, we took it one step forward because we need to ensure we're on the side favored by the equilibrium constant. Well, here we have initially a neutralization reaction, and that neutralization reaction is going to assume to proceed to completion. Once that's done, then whatever happens to be in excess is going to establish the equilibrium or establish the pH of the system. Because the volume is changing, it is much more convenient to work in moles. And so that is what we are going to do in this problem. Last day, we started this example and we did part A, and now we're going to do parts B, C, and D. So in part A, we determined the hydrofluoric acid concentration in the overflow, and I'm just going to flip over to the document camera where we can go through that and then continue on with B, C, and D. So this is the neutralization reaction associated with HF, and we were able to calculate that given the amount in the titration that needed, 18.63 milliliters of hydroxide, we can determine the number of moles of HF and then calculate the HF concentration in that overflow container. And that is what we did last day. Part B is to determine the volume of concentrated acid that was spilt. Because we're working with all HF, okay, we can use the equation C1V1 equals C2V2 because it's the number of moles of HF is the same on the left and the right hand side. And so we're going to say that this is our stock and this is our dilute. It really doesn't matter how you set it up. And we're interested in determining the volume of our stock solution that was spilt. That's C2V2 over C1. Plugging numbers in, you get 0.1066 moles per liter. And the problem tells you that the initial stock the concentration of the concentrated HF is 28 moles per liter. And when you do this and go through the math, what you find is that the volume of concentrated HF that was spilled is 9.52 milliliters, limited to 2 significant figures. That superscript C often refers to concentrated HF, basically as concentrated as you can make it. And just for the fun of it, if we go back over to here, yep, the camera is working. And you can see that that color on the left-hand side really hasn't changed. And the sodium hydroxide I was using, NaOHC, for concentrated sodium hydroxide. So that's about 15 molar sodium hydroxide that was put in there. Ow. Oh, that hurt. Okay. Part C is the one that's going to take us a bit because we have a number of calculations that we need to do. And we're going to start with the non-addition of sodium hydroxide, or 0.00 mils of NaOH. And of course, this would be our initial conditions. We don't have a neutralization reaction because we haven't added any sodium hydroxide, so we're simply left with HF being in equilibrium plus F minus. And we've previously calculated how much HF was spilt in our 10 mil aliquot. That was 1.066 times 10 to the minus 3 moles of HF. Initially 0 of those. And if we go and look up the Ka value, you get a Ka value of 6.6 times 10 to the minus 4 moles per liter. So we have this. We're on the side favored by the equilibrium constant, so it's simply minus x, x, x. Now, the ice table is in moles. We do need the total volume, and that total volume is 0.010 liters, 10 milliliters. Our Ka expression requires concentration, and concentration would be taking the number of moles and dividing by the volume, which is what we've got going on here. And because all of the volumes are the same, this equation simplifies to be that. When we substitute in numbers, you get this expression there. And to be honest, you could make the assumption that x is negligible, go through, solve it, do the check, and all that sort of fun stuff. You're free to do that, or what I find is that it is easier and faster to not make any approximations, rearrange it such that everything's on one line, and just plug it into solver. And if you do that, you find that x is equal to 8.08 times 10 to the minus 5. 8.08 times 10 to the minus 5. Now limited to 2 significant figures, thanks to the Ka value. If you were to make the approximation and solve it, you'll probably see the last digit change by a digit or two. But the 8.1 is not going to change. So what is x? We go back up and look at our ICE table, and we find out that x is the hydrogen ion concentration. That's good. Sorry, back up, I lied. X is the moles of hydrogen ions. It's not the concentration. X is the moles of hydrogen ions. So in order to get the concentration, we need to take and divide it by the volume, which is still 10 milliliters. And you find out that 8.08 times 10 to the minus 3 moles per liter is the hydrogen ion concentration, and that gives a pH of 2.09. Honestly, this is no different than what we would have done the other day when we were calculating the pH of many of these entities when we do this. So that calculation should have been something that you have seen before. When we have 10 mils of sodium hydroxide, we now need to worry about neutralization. Well, we need the number of moles of hydroxide, and that is the volume, 10 milliliters times the concentration, and that gives 5.72 times 10 to the minus 4 moles of hydroxide. So we have a neutralization reaction. And all of the numbers, even though we've added the hydroxide, the moles of HF are unchanged initially at 1.066 times 10 to the minus 3 moles. We just calculated the moles of hydroxide, and we don't need to worry too much about water. The limiting reagent here is the hydroxide because of the stoichiometry, and it's the smallest number. Okay, that means that we are before the equivalence point. We are before the equivalence point because our excess after neutralization will still be our analyte. Bad. Minus 5.72 times 10 to the minus 4. That goes down to 0. That's 5.72 times 10 to the minus 4. And this one on the left-hand side ends up becoming 4.94 times 10 to the minus 4 as well. That's the neutralization step. We still have an equilibrium that we need to worry about. We know that HF is in equilibrium with H plus plus F minus. And there was a question. Go ahead, Afrin.
So can you, like, Isabel just asked, and I also want to know, can you repeat why we're before the equivalence point?
Sure, not a problem. I didn't see her question. So why are we before the equivalence point? Because if we go to this neutralization reaction, remember that HF is our analyte. That's what we're titrating. And our titrant is the hydroxide. In this neutralization step, we use up all of the hydroxide, and so we have an excess of the analyte. And by definition means we haven't added enough titrant to reach the equivalence point with HF, which puts us before the equivalence point. Does that make sense, Afrin and Abigail?
Yeah, I think it does.
Isabella?
Sorry, so when we're at the equivalence point, are you, sorry, I'm just a bit confused still, so the analyte will be the one that's limiting?
No, the next one will be at the equivalence point, and you'll see why when we get there. Can you hold on for a few seconds, Isabella?
Yeah.
Okay, hopefully it'll make more sense when we get there. I have to finish this one, but the next one will be, I hate to break it to you, it's at the equivalence point. So, but it should make a lot more sense, and we'll come back and talk about that when we get there, okay? So, yep, I will come back to you. Setting up an ice table on this. We have numbers now. HF, the excess HF is 4.94 times 10 to the minus 4. And we still have 5.72 times 10 to the minus 4 moles of fluoride that have been produced. We have a mixture of a conjugate acid-base pair. This, by definition, is a buffer. And if it's a buffer, we can use the Henderson-Hasselbalch equation. Here, pH is equal to pKa plus the log base over acid. We do need the Ka value. That hasn't changed from the 6.6 times 10 to the minus 4 moles per liter. The pKa is 3.178. So the pH would be that, and this gives a value of 3.24.
Roy, could you I kind of forgot, but could you remind me again how you know when a question is a buffer question?
Sure. The question is, how do I know it's a buffer? When you have something that has a mixture of a conjugate acid-base pair. So there have to be appreciable amounts of each of the conjugate acid-base pair, HF and F minus in this case. And so here, as soon as we saw that when we're putting initial values of HF and F minus into each of these columns, that by definition is a buffered system. Does that answer your question, Afrin?
Okay. Yeah, it does. Thank you.
And we talked about it the other day, but just as a reminder, this can be a concentration ratio. It can be a mole ratio. And we saw the other day, or we showed, that the concentration ratio equals the mole ratio because the volumes just cancel out. As a matter of fact, once you get comfortable with this, you can sit there and look at this and go, okay, wait a second. Let me just delete a few things. I have a buffer. instead of rewriting it out and just doing the same thing and saying, hey, buffer, you can look at the products of your neutralization reaction, and this is the products of the neutralization reaction. And all we're going to do is we're going to transcribe them down here. And if you're comfortable and understand that, hey, I can look at this and go, oh, well, look, conjugate acid-base pair, buffer, I don't need to rewrite it out and say the same thing. Just as you get more comfortable, you can start taking a few steps. Similarly, down in terms of the calculation, all this line does is it retypes out the numbers that are already up above. So if you're comfortable not writing this in because it's redundant to a great extent, you can jump from the pH down to, from the Henderson-Hasselbalch equation down to the end product. This actually came up in the last class where I accidentally transposed the numbers. I had 4.49, not 4.94. And it was pointed out to me by a student that, oh, that I did that. I'm like, oh, that's great. But if someone hadn't been paying attention, I could have typed it into my calculator wrong. Why repeat numbers if you don't need to? And again, once you get comfortable, there's really no need for that line right there. That just takes time, but realize that I'm showing you all of the steps, what I expect to see. But I don't need to see all of them on an exam as you get more and more comfortable with it. Okay. I hope that makes some degree of sense. Isabella, Afrin, and probably a few other students. Let's continue. 18.63 milliliters of sodium hydroxide. All right, need to figure out the number of moles of hydroxide. Number of moles of hydroxide is 18.63 milliliters times the concentration gives that many moles of hydroxide. So now we have to look at the neutralization reaction. Again, the number of moles of HF not going to change. 1.066 times 10 to the minus 3. The moles of hydroxide is changing because we're adding volume, but it is now 1.066 times 10 to the minus 3. Isabella, Afrin, or anyone, how do I know that I'm at the equivalence point?
Is it because there's equal volumes now for moles?
Yep. It means because, that's a good point, should put my units over on the right hand side. The equivalence point is defined as the point where you have a stoichiometric equivalence of your analyte and your titrant. And so they're now equal. And so both of these drop to 0. They are all gone. And you're left with the only thing left in solution is the conjugate. So because these drop to 0, we are at the equivalence point. That's bad. I don't know how to get out of that. we are at the equivalence point. And what controls the pH? The conjugate. That's the only thing we have anything of, is the conjugate. And we know, because HF is weak, that fluoride will hydrolyze in water. Oops. Yeah. No, I did it right. Good. Now, here, we do need a Kb value, and I'm just going to give you the Kb value. Is 1.5 times 10 to the minus 11 moles per liter. We've calculated Kb values before. Leave that to you. In terms of values, 1.066 times 10 to the minus 3. Don't care about the water. And so when we do this, x minus x we have all of this. Remember, the ice table is in moles, and we do need the total volume as well. The total volume is our 10 mil aliquot plus the 18.63 milliliters of sodium hydroxide that needed to be added. So this is 28.63 milliliters. So our Kb equation would be the number of moles of HF times the number of moles of hydroxide, number of moles of fluoride times the volume. We just went through how that comes to pass. And so when we plug numbers in, we have 1.5 times 10 to the minus 11 is equal to x squared over that. Again, you could make the approximation and do all that sort of fun stuff. I'm just going to sit there and say I'm using solver. And solver is going to give me an x is 2.144 times 10 to the minus 8. Whew. If I go back up to my ice table, X is the moles of hydroxide. So if I have the moles of hydroxide, I can calculate the hydroxide concentration. As such, that gives a value of 7.49 times 10 to the minus 7 moles per liter, which gives a pOH of 6.13 and a pH of 7.87. Go ahead, Isabella.
Chris, probably gonna be a really dumb question, but so in the ice table for the 10 milliliters, for the second one, how you like disassociated the HF, how come it was different for this one? Like, why did you use a different equation?
Because I don't have at the end of this neutralization step, I don't have any HF. What I have is a weak base.
Oh, okay. Okay.
Right? So realize the fluoride has the acidic reaction, and that's what we used previously. The idea of HF is in equilibrium with H plus F minus, or the basic reaction, and that's the one we used here because we're starting with F minus, not HF.
Okay.
Good? Good question. Excellent. Okay, one more. 25 mils. How many moles of sodium hydroxide are there at 25 mils? Go for it. Exact same calculation. Type your answers into the chat. Okay. A couple people are getting 1.43 times 10 to the minus 3 moles of hydroxide. And they are correct. So the neutralization reaction is here. And again, the number of moles of HF isn't changing. Moles of hydroxide are there. Now our limiting reagent is, of course, HF. That goes down to 0. And fluoride, of course, is easy to do. The center one leaves us with 3.64 times 10 to the minus 4 moles of hydroxide. So here we have a strong base and a weak base. We've already done the calculation with acids to show that if you have a strong acid and a weak acid, this is when we did the sulfuric acid, the strong acid dominates. The weak acid doesn't contribute to the pH. So here, we only need to worry about the strong base. And so the hydroxide ion concentration is 3.64 times 10 to the minus 4 moles of hydroxide over our total volume, which is 0.035 liters, 35 milliliters. That gives a hydroxide ion concentration of 1.04 times 10 to the minus 2 moles per liter. And a pH, or sorry, a POH of 1.92 and a pH of 12.02. 1.98, excuse me. All right. Of course, because I have an excess of hydroxide, this must mean I am after the equivalence point. That is to say, I have an excess of my titrant, I'm after the equivalence point. I know I'm running short on time, so I just want to quickly graph this. I think that's about right. So in terms of these calculations, our initial pH was 2.09, which is right there. After 10 mils, the pH was 3.24. After 18.63, it became 7.87, which is about right there. And after 25, it was 12.02. So if you were to draw a titration curve through this, it would look something like this. That bad. That's better. When a computer does it, and the numbers are off by a little bit, I can't remember why the numbers are off by a little bit, but the titration curve is consistent. This just has a little bit more information on it. At the before the equivalence point, of course, you have a buffered region, and at the half equivalence point, that would be about 9.3 milliliters. You have pH equals the pKa at that point. Yeah, and so this is what the titration curve looks like. This is the titration of a strong base with a strong acid, of course. This is always left as a student exercise, so I would like you to go through and practice this. What I hope you find as you go through and do this is that it's the same calculation again and again and again in terms of these calculations. It's the same process that you need to get comfortable with, figuring out what's in excess, figuring out whether you're before, after, or at the equivalence point, and then, of course, determining the pH appropriately. So I will post the answer to this up on Blackboard. If it's not already there, it will be made available. I want to finish by summarizing this chapter, so bear with me for about one more minute. I would appreciate it. We have a buffered system, which contains a weak conjugate acid-base pair and resists changes in pH, as we saw with the demonstration earlier today. The buffered range exists around the pKa value, and it's plus or minus 1 on that pKa value. You can ignore the line on buffer capacity. It's not something we covered in this course. We do have a number of acid-base indicators, and all they are is weak acids that are colored in one or both of the acidic or basic forms. And of course, the midpoint is the pKa value. And this last slide summarizes all of the calculations associated with with titration, acid-base titrations. Whether you have a weak analyte or a strong analyte, you can calculate the pH initially, before the equivalence point, at the equivalence point, and after the equivalence point. So this summarizes everything that we've done up to this point in time. And that actually concludes chapter 17. We still have chapter 18 to do, which we're going to complete Wednesday and Friday. And then you will be done all of the material for problem set 4. Does anyone have any questions? Everything makes some degree of sense. Given what's being posted to the chat, it looks like everyone's comfortable with that. All right, ladies and gentlemen, if you have any questions, please get a hold of me. Otherwise, have a great evening, and I'll see everybody on Wednesday. Take care.